Hi guys, today I would like to derive mathematical expression for the capacitance of a capacitor. Let's recall about capacitors. So here what we are seeing, so these all are DC capacitors. So capacitor is a charge storage device. It can store charge. So not only that, so later we will understand that it will store potential energy also. So when the charge stores, so because of that potential energy also gets stored. So this is an energy storage device, and we learned the capacitance of a capacitor formula: C equal to charge upon potential difference. Charge by potential difference, in terms of we can express it's a Q upon V. If I write the units, charge units are coulombs, potential units are the volt, so which equal to coulomb per volt inverse, which is the capacitance units. Now this capacitance comes different sizes and different varieties. So let's first derive what is the expression for mathematical expression for capacitance of a simplest case we will take capacitance of a parallel plate capacitor. So let's derive capacitance of parallel plate capacitor. So let's recall what is a parallel plate capacitor. So capacitor is a setup. So here parallel plate, so here I need one charged plate. Let me take this as a positive charge, and if I take one more plate, so this is my another plate which is having negative charge, so the negative charge on it. If they are separated with a distance d, the d is the distance between the two plates. If we can express it is having surface charge density, because it's a plate, we will express that in terms of surface charge density positive sigma, and it is having surface charge density negative sigma. And this whole setup, if we can take that as a whole setup, and if we can highlight this, so this setup we are calling as a capacitor, especially in this case parallel plate capacitor, because here the conducting plates what we taken are the two conducting parallel plates. Now to this case I would like to derive the what is the capacitance for this capacitor. For that, so let me recall, suppose if it's a positively charged plate. So if I draw a positively charged plate at here, so let me take this as a positively charged plate. So let me recall our previous knowledge. So by using Gauss's theorem, so we derive the electric field in this region. Suppose if I draw the electric field lines due to this positively charged plate, so that is something this look like this. So it's a positively charged plate, and if you want to express the electric field in the two sides, the expression for the electric field E equal to sigma by 2 epsilon naught. And if I take the negatively charged plate also, since we know the electric field because of the negatively charged plate, so here the electric field expression changes to electric field E equal to minus sigma by 2 epsilon naught. The two sides, any side you can take it. So here the negative sign tells about the direction of the electric field. So here the positive sign tells about the direction of the electric field. And we are having this knowledge, and by using this knowledge of the electric field, so we will try to derive the capacitance. And the capacitance having the formula C equal to Q upon V. And to get the V, I would like to recall one more formula at here itself. The relation between electric field and potential. Electric field and electric potential relation. So if you remember that, so we can write that as electric field E equal to minus dV by dr. So here the r is the small distance. Suppose in this case, if I take only the magnitude, so I can take the modulus in this case, and the minus sign tells about the direction of the electric field. Where the potential decreases, so there will be the direction of the electric field. Now in this case, if I take as a whole, so here the dV tells about the small elemental potential and the dr equal to small elemental length. Here that I will convert in terms of the distance. So for that, if we take dV equal to total potential V and the dr equal to the distance between the plates d. So we can write the expressions E equal to V upon d. So I can use these expressions later, E equal to Vd. So this is the relation between electric field and electric potential. Now let's understand my strategy. So to derive this formula, the electric field, the capacitance of a capacitor formula. So here the Q is the what is the charge on the plate, that we will understand, and we need to derive the potential. So how can I derive the potential? First I will derive the electric field. So let's derive the electric field between the two parallel plates. So for that, let me take this as a setup. So this is a positive charged plate having positive charge density, and this is negative charged plate having negative charge density minus, and they both are separated by a distance, separation distance d, and between nothing is present. For a moment we can take as air is the medium. Now if you write the expression for the electric field on the left side, on the right side, in the inner region, and the electric field on the left side which is equal to 0, and the electric field on the right side which is also equal to 0. Why? Because if you can observe this electric field lines clearly, on this left side, on this right side, the electric field strength is equal and opposite. Or if you can write the expression for the electric field properly, for this green arrow, that is the positive charge, electric field due to positive charge which is equal to sigma by 2 epsilon naught, and for the red arrow mark, electric field to the negative charge, if you can write, that is the minus sigma by 2 epsilon naught. If you can write the electric field total, so that equal to E plus and plus of E minus, so the total electric field goes to 0. Similarly, the same thing happens on the right side here also. So the total electric field in these two regions, that will be 0. And we don't need that also, because the capacitors do not require the left side and the right side. The capacitor which more we need that inner region. So this is the region we need to concentrate, in the middle region. Now I need to find out what is the electric field within this inner region. Now by seeing this arrow marks, we are understanding the electric field will be add up. Now in this case, if you can write electric field which is inner region, that I can write sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So here the inside the region, the two electric fields are the sum. They should be add. So if you can write the total electric field which is inside, so that In the place of inner, I supposed to write the total. So electric field total, which equal to sigma by epsilon naught. So if you can substitute the sigma value, sigma is nothing but surface charge density. Since sigma equal to surface charge density, charge per unit area. So electric field total, which equal to Q by A epsilon naught. So this is my first electric field expression, the electric field which is present between the two plates. Let me take this as equation 1. And just above here I derived the relation between electric field and electric potential. So if you remember this formula, electric field and electric potential, electric field equal to minus dV by dr. So that is the relation between electric field and electric potential, and we got an expression potential V equal to ED. So let me take this as an expression 2. Now you can substitute that 1 into, so if you can take 1 into, so the 2 expression V equal to ED. So in the place of E, you can substitute this value at here, potential V equal to Q by A epsilon naught times D. Now this is the final potential expressions what we got, or strictly we can say that potential difference expressions. And if you can directly substitute this expression in the formula, capacitance formula, capacitance C is equal to Q upon V. So C equal to Q upon, in the place of V you can put this value at here, so which gives us a Q by A epsilon naught times D. Now you can cut the charge. The final expression you can get C equal to epsilon naught A upon D. So this is the expression for capacitance of a parallel plate capacitor. So the great thing in this expression you can see, so there is no charge in this expression and there is no potential difference in this expression. Now the capacitance of a capacitor is purely changed. The capacitance is directly proportional to area of the plate, and the capacitance is inversely proportional to distance between them. Now if you can combine that, we can write capacitance C directly proportional to A by D. We will remove the proportionality constant C equal to epsilon naught A upon D. So this is the handy expression to remember. So that's the reason why the capacitors are having wide varieties and the different sizes, because the capacitance formula C equal to epsilon naught A upon D. To increase the capacitance, either you have to increase the area or you need to change the medium permittivity, or you need to decrease the distance between them. Suppose if you want to prepare a capacitance of a capacitor C equal to 0.22 microfarad. So that is this is a small tiny one. So if you can highlight, so this is the tiny one. So here it is showing the capacitance of a capacitor. So 0.22 microfarad. Now, so to prepare this one, so we need to know what is the area of the plates and what should be the distance between them. So the capacitance is purely depending upon these two factors, either the area and the distance between them, or if you can change the dielectric medium, so epsilon naught, instead of the air if you can keep some other, so later we will understand. So if you can change the epsilon naught also, so the capacitance value gets changes. Now here you can see the very big capacitor, which is the blue, which is having the 1500 microfarad, capacitance equal to 1500 microfarad. If we want to prepare this much capacity of a capacitance, either we have to increase the area of the each plate, or we need to decrease the distance between the two plates. So that's the easy formula, how the capacitance formula Q upon V changed in terms of C equal to epsilon naught A by D. So this is the final expression for capacitance of a parallel plate capacitor. I would like to visualize how this capacitance change with the area and the distance with the help of the PHD stimulation. So let me take it here. I'm having certain help of the graph. So in this graph, so it shows about what is the capacitance of the capacitor. Suppose if I charge, so now the capacitor is charged. So let me take the charge also, electric field. So that is the electric field between them. Now the capacitor gets charged. Now with the help of this arrow mark, suppose if this is the dimensions, so here the dimensions between mentioned that, so the distance D equal to 6 millimeter and the area A equal to 200 millimeter square, and the medium here the epsilon naught equal to air or vacuum, it's having as an almost all one value. You can take that as a one value. Now if this is the dimensions, so what is the capacitance? Here you can see the graph here shows the capacitance value. So the capacitance value C equal to 0.30 picofarad. Suppose if I change either the area, if I can decrease the area. Now here you can observe, now the area is decreased to 100 millimeter square and the distance is same. Now the capacitance decreased. Now here the capacitance value decreased to 0.5 picofarad. If D equal to 6 millimeter, 6.0 millimeter and the area A equal to 100 millimeter square. Now let's change the distance. Suppose if you change the distance between the plates, now the 6 millimeter is little high, so I would like to decrease the area, I would like to decrease the distance. If I can decrease the distance at here, now in this case the dimensions are distance D equal to 2 millimeter, 2.0 millimeter and the area equal to 100 millimeter square, and here you can see the capacitance value C equal to 0.44 picofarad. Now the capacitance is increased. So the capacitance of a capacitor either increases or decreases, and if you can, in this case, if you can increase the area and you can decrease the area, or if you can increase the distance or decrease the distance, so the capacitance value gets changes. So that's the main reason why the capacitors are having the different sizes, because to change the capacitance of a capacitor, so the one and only thing, either you have to increase the area of the capacitor or you need to increase or decrease the distance between the two plates for a parallel plate capacitor. So finally, today we learned about the capacitance. We started with the capacitance of a capacitor formula. So that is the capacitance C equal to Q upon V. So this formula, for a moment I converted that in terms of C equal to epsilon naught A upon D. So here the D is the separation distance and the A is the plate area, and the epsilon naught is the permittivity, means the medium which is the present between the plates. If you can take this medium as an air medium, so that is the air is the medium, so these three parameters will affect the capacitance of a capacitor.